Hello everybody. There we go. That's a little bit better. All right. I think I've got this in a good place. It's a little crooked, I know. I'm working on it. Hi everybody, I'm meteorologist Meghan Danahey. Hello, hello. I have a microphone today, so my audio should be a little bit better. But welcome to Let's Weather Together, the third edition here as we move through some homeschooling. It's a great opportunity to bring some of the material that I usually take on school visits to the kiddos and even you adults at home. It's just a fun way to look at the weather and some of my favorite things about the weather. It's fun to just sit here and be able to talk about those. So today we're going to talk a little bit about severe thunderstorms. On Tuesday, we talked about just regular air mass thunderstorms. We also talked about layers of the atmosphere. Remember that? So on Tuesday, we talked about the 5 main layers of the atmosphere: the troposphere, the stratosphere, the mesosphere, thermosphere, and exosphere. So there's 5 layers of the atmosphere, and all of our weather, of course, happens in that lowest level of the atmosphere, in the troposphere. That's about 10 miles or so thick. Now remember, Mount Everest, we talked about Mount Everest on Tuesday, is roughly 5.5 miles tall, or about 29,000 feet. And our thunderstorms can grow between 40,000 and 60,000 feet tall. So they can be twice as tall as Mount Everest. We talked about that on Tuesday. We also talked about weather balloons. They are launched, like this one here. They are launched from 92 different locations around the United States twice daily. And remember, they have a radio sound on the bottom, which has a whole bunch of instruments. It measures temperature, it measures humidity, it also measures wind speed and wind direction at certain points as it travels up in the atmosphere. And it can climb about 100,000 feet or so. So that's our weather balloons. That data is, of course, transmitted back to the National Weather Service, where it's plugged into models, and we can do forecasts for aviation, for marine. We can also help predict severe weather. Weather balloons are really important when it comes to severe or dangerous weather. And so that's what we're going to talk a little bit about today, is what happens in the upper levels of the atmosphere that can give us severe thunderstorms. This is a little bit of a review of what we talked about on Tuesday. All thunderstorms, this would be just kind of a garden variety thunderstorm. All thunderstorms have that updraft and downdraft. Now, the basic ingredients for a thunderstorm, we talked a little bit about this on Tuesday too, are instability. So what is instability? Try and imagine you're swimming in a pool and you have a basketball. And you're going to hold your breath, you're going to take that basketball and push it all the way to the bottom of the deep end of the pool. What happens if you let that basketball go? It rushes to the top, right? So that helps define instability. Imagine that basketball is a parcel of air and it wants to rise. So instability is an ingredient that we need for thunderstorms, as well as moisture. We got to have moisture. We got to have water vapor to be able to condense into clouds. So we have to have moisture, otherwise known as high humidity. We need that too. And we also need a lifting mechanism. We need something to get the air rising, right? We've got to get the air rising. And that could be a front, a cold front, a warm front. We actually have a warm front coming through the St. Louis area today, and it's going to try and produce a few showers. A warm front gradually lifts the air, where a cold front gives us more dramatic uplift. You tend to get more thunderstorms along cold fronts and more stratiform kind of rain, gray rainy days, with warm fronts. But a lifting mechanism is needed, and that could be an area of low pressure. We talked about low pressure on Tuesday as well. So we've got all the ingredients that come together. We get rising air. It takes our cumulus cloud into a towering cumulus cloud, and eventually we have a mature thunderstorm. All thunderstorms have that updraft and that downdraft. So that's what all thunderstorms have. And we talked about on Tuesday that this generally will rain itself out in less than an hour. These thunderstorms can last 15 minutes up to an hour. They'll rain themselves out because the updraft is sitting right next to the downdraft. So that's a garden variety storm. I'm going to show you now what a severe thunderstorm looks like. And I just want you to know that I see you guys when I come over here and I'm looking at my phone. Hi Dana, your daughters are watching, so I can see some of you here. But when I'm at the whiteboard, I can't really see the phone. So let me show you now the ingredients for severe. Our garden variety storm and a severe thunderstorm are different. We need an additional ingredient. And let me point one other thing out here really quick. Our weather balloon, remember, it's measuring the wind direction and wind speed at different altitudes in the atmosphere. So as that weather balloon goes up 10,000 feet, 20,000 feet, 30,000, 40,000, 50,000, 60,000, it's measuring the wind direction and wind speed. And so I've got that represented here. So in our garden variety thunderstorm, winds aren't changing with height much. We're seeing kind of the same wind direction and kind of the same wind speed. So we don't have a whole lot going on with the winds. That's the additional ingredient that we need for severe thunderstorms. So I'm going to pull this over and bear with me while I make sure you can see the other side. Okay. Hello, Debbie. Hi, Stephanie. All right. So there's a little bit of a difference here. My camera stand is not happy today. It's a little crooked, and I'm afraid it's going to fall over. But hang on with me, guys. Okay. So here's the difference in our severe thunderstorm. I'm trying to get it to where you can see both of these. All right. So the other ingredient that we have that gives us severe thunderstorms is called shear. It's called wind shear. And we can have that in two different forms. You can have something called speed shear, or you can have directional shear. And all we're talking about here is that weather balloon. Remember, as it goes up, it's taking wind speeds and wind directions. So as the weather balloon goes up, in this situation, it's finding that our wind speeds are increasing with height. So maybe down here the wind is at 15 miles per hour, and maybe here it's at 25 miles per hour, and maybe here it's at 45 miles per hour, and maybe up here it's at 70 miles per hour. We're still seeing, maybe let's say it's a wind out of the south. So the wind direction is the same as you travel up in the atmosphere, but the speed is increasing with height. Our winds are blowing faster as you climb. 15 miles per hour, 25 miles per hour, 45 miles per hour, 70 miles per hour. So do you think when we get a rising parcel of air, remember our basketball at the bottom of the pool, do you think that when that air is rising that it's going to go straight up with these winds? Or do you think it might lean over just a little bit? That's what this speed shear does, is it tilts the updraft. The updraft leans over. And it separates the updraft part of the storm from the downdraft part of the storm. Let me get out of the way. You see the difference in these two? See the difference? In our first example, the updraft is right next to the downdraft. They're right together. The storm rains itself out. In this example, where we have speed shear, or winds increasing with height, we have a tilted updraft that is now separated from the downdraft, and this thunderstorm can live a whole lot longer. Remember that? We talked about this storm running out of gas. The rain cuts off the updraft, and it will rain itself out. So speed shear will allow a developing thunderstorm to tilt, which separates the updraft from the downdraft. It creates a stronger storm that can live longer. It can live longer. Since the updraft and downdraft areas are separated in our tilted thunderstorm, our tilted thunderstorm, this one over here, has constant access to this warm, unstable, moist air, all those ingredients we need for thunderstorms, and it can keep going and going and going. It's kind of like the Energizer Bunny. Remember the Energizer Bunny? So that's how this thing can keep going. And these types of storms can grow larger hailstones, They can develop stronger winds at the surface. But we need another ingredient for tornadoes. So our ingredients so far are instability, moisture or humidity. We also need a lifting mechanism. And now we have speed shear, which gives us severe thunderstorms. But there's another ingredient I want to talk to you about that gives us tornadoes. So what would maybe give us tornadoes? What extra ingredient do we need? Let me set my camera view again here. I want to go to this side first. All right, so here's a review on our wind shear. Think of it this way. Wind shear equals severe. That's that extra ingredient that we need to get misbehaving thunderstorms. We just talked about speed shear. Speed shear is the wind speed increasing with height. So we have faster and faster winds as you climb up in the atmosphere. It tilts our updraft. Directional shear. That's the second bit of wind shear that I want to talk to you about. Directional shear. Directional shear means that the wind direction is changing with height. So here at the surface, we have a south wind. If you go stand out in the driveway and you feel a south wind in your face, that's the wind at the surface. But our weather balloon, as it climbs, finds a north wind aloft or higher in the atmosphere. So wind direction is changing with height. And that sets up a motion in the atmosphere like this. It's a horizontal spinning. Kind of as I roll this pencil or roll this marker, because the winds are changing with height, you get a rolling motion. You could do the same with a paper towel roll would be better, but it basically creates a horizontal rolling motion, just like that. Okay? So our directional shear creates these tubes that are spinning. Well, what do you think happens if our thunderstorm comes along, our towering cumulus comes along, and it pulls one of these things up into the updraft? So we have horizontal spinning. It's pulled up into the updraft. Now what do we have? We have vertical spinning. Does that make sense? Let me check in on you guys. How are we doing over here? Hi, Becky. So our horizontal motion gets pulled up, and now we have a vertical spinning, and our whole updraft is rotating. So you really need directional shear to even have a chance for tornadoes. And now, just because we have that vertical spinning, it doesn't mean we have a tornado. It means we have a rotating updraft. And a rotating updraft, those are the storms we really, really have to watch. We really have to watch those. Let me just check on my notes here, make sure I'm covering all this stuff. All right, so we talked about directional shear. Speed shear, wind speeds increasing with height. Directional shear, wind direction changing with height. All right, so we're talking about that rotating column of air getting pulled into the thunderstorm, and that's not a tornado yet. But here's what happens. Let's go back over to, let me see if you can see this thunderstorm example now. Let's turn it. Sorry. Hey. All right. So now we're going to talk about, this is an example of hi Dana. This is an example of a supercell thunderstorm that I've drawn. And we're going to talk about the different parts of this. But what's happening in the supercell thunderstorm is that our updraft, all this air that's going up, is now rotating vertically. Okay, it's rotating vertically. And remember, our updraft is tilting. It's going off to the side. So that rotating updraft is getting stretched thinner and thinner as the storm rises in the atmosphere. That rotating column of air is getting stretched thinner, and it spins faster. If you ever watched during the Olympics, like ice skaters, as they spin around, and they're kind of spinning around slowly with their arms out, but as they pull their arms in, they can spin really fast. Kind of the same thing going on in our supercell thunderstorm. That rotating updraft is being pulled and being stretched in the vertical, and it makes it spin faster. And a lot of times, our radar can see that storms are spinning. we can see the direction of air particles in the middle of the storm. And so we know if a storm is spinning, but we usually know if it's spinning somewhere in the middle. Spinning at the surface is where we have our tornado. And that is why we have a tornado, is we have this rotating column of air. So what is a tornado then? If we have a rotating updraft, we don't necessarily have a tornado. A tornado is a rapidly rotating column of air that is in contact with both the cloud and the ground. So let me repeat that. A tornado is a rapidly rotating column of air that is in contact with the cloud and the ground. So a tornado is air. Can you see air? No, you really can't. You can see stuff in the air, right? You can't really see air. So typically, here's what we see. We've got this rotating updraft. It's getting stretched thinner and thinner. It's turning faster and faster. And perhaps we now have rotation at the bottom of the storm that's becoming more evident. The first thing that you'll see is a wall cloud. I've tried to draw one here, but it looks like a wall. And it's attached to the bottom of the thunderstorm. Generally, there's no rain around the wall cloud because it forms in that updraft area. Remember, our updraft is here, and what do we have in the downdraft? We have rain. So usually our wall cloud is also, it can be spinning. You can see them spin, and it's attached to the bottom of the cloud. Usually the next thing we'll see after a wall cloud is a funnel cloud. I'm sure you've heard of a funnel cloud, right? So a funnel cloud is exactly that. It's a cloud. You're actually seeing condensation in the shape of a funnel. It's coming this way. You're actually seeing a cloud being formed. A tornado, the funnel cloud, is a cloud. The other thing that you might see is debris here at the surface. If you have a rapidly rotating column of air that's in contact with the ground and is picking stuff up and blowing stuff around at the surface, you have a tornado. Remember, rapidly rotating column of air in contact with the cloud and the ground. So we actually see a tornado by two things: that condensation funnel, that tornado-looking cloud, and debris. It's debris, it's stuff blowing around in the tornado that gives them that dark appearance. It's dirt, it's parts of trees, parts of fences. So what we actually see in the tornado is a condensation funnel, and it's also debris that's been picked up at the bottom. So that's pretty much what you, I mean, there are a lot of ingredients for tornadoes, and honestly, we don't know everything about how tornadoes form, because we can have 1 out of every 4 of these storms will actually produce a tornado. A lot of these rotating supercells will rotate all day long for hours. They live for hours. Remember this other storm that we showed you, that rains itself out in 15 minutes to an hour. These storms can last for hours and hours and hours. And sometimes they never produce tornadoes. When they do produce tornadoes, sometimes they can produce multiple tornadoes because they live for so long. So we talked about the damage at the surface, the wall cloud. We talked about how it gets that color and how we can see it. Some of the most powerful tornadoes on Earth have winds over 200 miles per hour. Do you know the fastest wind speed ever recorded in a tornado? Let me peek over here and see if anybody has any answers. Do you know the fastest wind speed that has ever been recorded in a tornado? You guys still have me? It says I'm losing my signal. 301 miles an hour. A measured wind speed of 301 miles per hour in a tornado near Moore, Oklahoma back in 1999. Now here's something else. You can't look at a tornado and say, oh, that's an EF5 coming right at me. What is an EF5? Tornadoes are rated on a damage-based scale. because we don't have any instruments that can get right up close to this thing and really survive. And not to mention, do you want to be right up close to this thing? I know I don't want to be right up close to this thing. But so tornadoes are actually rated on a damage-based scale. What happens, let's say we have a whole bunch of bad storms roll through today, this afternoon, maybe into the overnight, and we have damage out there. The National Weather Service sends out survey teams, meteorologists, just like me, who are trained to look at the damage and rate what the wind speed must have been to do that damage. So if it's just a little bit of tree damage, it's a weaker tornado. If perhaps the roof is ripped off but the house is still there, perhaps it's a stronger tornado. And then you can have really powerful tornadoes that clean and sweep foundations. And that's the enhanced Fujita scale. So it's a damage-based scale where we estimate the wind speeds in the tornado. So when you hear us say the day after that the tornado was confirmed as an EF2 with winds of 130 miles an hour, that's what we're talking about, is the enhanced Fujita scale. And that's named after Dr. Fujita, who was a very prominent atmospheric scientist and severe storms researcher. So the EF scale, I have it here for you. I'm not sure if you can see it. Let me pull it up close here. There's your EF scale. So a weak tornado is EF0, 65 to 85 miles per hour. And then you can see it steps up from there. EF1, EF2, EF3, EF4, EF5. So anything over 200 miles an hour is a EF5. So that's the EF scale. All right, let's talk about some of the other things that you're seeing in this picture. You guys, can you hear me okay? Everybody getting audio and visual okay? I know that a lot of stress is on the internet with a lot of people at home, and so I'm just wondering, I've got some people saying what's going on. Can you hear me okay? All right, so this is my Supercell Thunderstorm that I've drawn, and we can talk about some of the different parts of this storm and some of the different things we're looking at. Obviously, we've talked about the updraft region. What do you think this is right here? Any guesses? This is called an overshooting top. Remember when we talked about the layers of the atmosphere and we have our rising air that's going up in the thunderstorm? Everything that goes up, I think I did this on Tuesday, everything that goes up comes back down, right? So you get to a point in the atmosphere where you are stable, where the air parcels become stable and they start to fall. But this is such a strong thunderstorm, and you have such a strong updraft, that some of those particles actually shoot through that stable layer. So they actually punch right on through what should be the top of the storm in that stable layer, and that's what gives you an overshooting top. And sometimes when you're storm chasing or when you're out storm spotting is what it should be called, you're looking and observing at these storms. If you're at a pretty good distance away and you see an overshooting top that sits on top of that flat anvil cloud, you know it's a strong thunderstorm because it takes a very strong updraft to shoot through that stable layer. And an overshooting top can easily tell us that that storm probably has hail because strong updrafts equal large hail. And we're going to talk about hail too. So that's an overshooting top. Has anyone ever seen Mimatis clouds? They are my favorite clouds. Mimatis clouds. Anybody ever seen those? Mimatis clouds. I've got some pictures for you. They look like little pouches. They look like little pouches. They are my favorite clouds. Take a look at this here. They look really freaky sometimes. Mimatis clouds. I've got some more. Take a look. Mimatis clouds. Cool pockets of air. It's actually sinking air. These are some of the, actually I think they're the only clouds that are formed by sinking air. We talked on Tuesday that we need rising air for cloud development. These clouds are actually formed by cool pockets of air that are sinking, and they're usually at the top. So they're usually on that anvil. They're on the underside of it. And so a lot of times people say Mimatis clouds mean severe weather. Sometimes they can. Sometimes they mean it's coming. You can see it in the anvil as the storm's moving in. Sometimes it's as the storm is moving away. You can see these Mimatis clouds. But those are my favorite clouds. One more look at Mimatis. Love those. Favorite clouds. They're really pretty too, especially when the sun is setting on them. Oh, I've got more. I printed a lot of these just so you guys could take a look. Mimatis clouds are awesome. Well, I think they're awesome, but I'm also kind of a weather geek, cloud geek, right? I fell in love with the weather in 4th grade. And I remember I got a camera just so I could take pictures of clouds, but those are some Mimatis clouds. All right, so let's get back to some of these other things. So we have updraft, strong updraft, overshooting top. This top flat part's called an anvil. And then we often have Mimatis clouds underneath that anvil. We talked about this the other day, our downdraft, right? Our downdraft. Sometimes it spits out rain out front, very heavy rain, cold rain too. And of course we've got hail in there, right? We've got hail in there. So let's talk a little bit about hail, because I know you're probably interested in how hail forms. So we talked a little bit about how tornadoes form. We got to have a rotating updraft, and we have to have a rotating updraft, and we have to have that updraft tilted in the atmosphere where it's spinning faster and faster. And that gives us the issue at the bottom, that rapidly rotating column of air that's in contact with the cloud and the ground. That's our wall cloud. Sometimes these can become wrapped in rain. Remember, the whole storm is rotating, and so sometimes you can get a curtain of rain that's drawn around the tornado, makes them a little more dangerous. Let's talk about hail. Hail forms in this updraft region of the thunderstorm. That's where it's formed. Hail specifically comes from thunderstorms. Sleet is also ice, but it comes as a form of wintry precipitation. So hail specifically comes from thunderstorms, and it's formed in that updraft region. And it's pieces of ice, it's super cool droplets, it's water droplets that freeze onto something. They need to freeze onto a particle of some sort, a dust particle, an insect. I used to tell the story of Mr. Fly. You want to pretend that a fly's been sucked up into this thunderstorm? Mr. Fly. In fact, let me switch this because I have a lot of space back on this one behind me. Bear with me. Da, 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 da. And we'll talk about how hail forms here. Can you see the big storm? Okay. Cool. All right. So we have a little fly, Mr. Fly, and he gets sucked up into this storm. All right? Now, somewhere up in here, and it can vary, you have what's called a freezing level. Anybody know the freezing, that magic number in Fahrenheit, what our freezing temperature is? In Fahrenheit, it is 32 degrees. 32 degrees. So here goes Mr. Fly. You figure he's wet because he's been sucked up into this thunderstorm and he's in there with all those cloud droplets. Mr. Fly has got lots of water on him. Uh-oh. He goes up above this freezing line. What happens with the air temperature as we go higher and higher in the cloud? We talked about it on Tuesday. As we go higher and higher in the atmosphere, in the troposphere, temperatures are dropping. It's getting colder. If you could stick your arm outside of an airplane window, it would feel really, really, really cold. But you can't do that. You can't stick your hand out an airplane window. But if you could, it would be cold up there. So as Mr. Fly goes up into that storm, the layers of water that are on him probably freeze. So he probably freezes into an ice pellet. So Mr. Fly is now an ice pellet. And Mr. Fly goes up, and he gets maybe caught in this downdraft, and he goes down here where it's a little bit warmer. Maybe he gets some more water on him. Maybe he bumps into a few other hailstones, and he gets caught in this strong updraft again, and so he goes back up. So he goes down and up, and down and up, and down and up, and down and up. And that is how hailstones form in these storms. They get thrown up and down. It's a very violent atmosphere in here. They get thrown up and down and up and down, and they either develop layers of ice around that original stone, or they glom up together. Have you ever gone to get ice out of your freezer and there's maybe 5 or 6 cubes all stuck together? Hailstones can do the same thing. They're bumping into each other in this big storm, and so you can also have hailstones that actually all join up together and get really kind of spiky. So the hail size, this may make sense to you because it goes up and down and up and down. If our updraft is really strong, then our hailstones will be larger, right? That seems to make sense because they're being held up in that storm by the updraft. So as our hailstones are going up and down and up and down, and this is a strong updraft, then our hailstones are getting bigger and bigger. And I was taking a look at this. This is interesting. Our updraft strength. Let's see if you can see it. There we go. Our updraft strength. So in just a regular old updraft, so in our other storm, in this one, in that regular old updraft, the air is going up into that storm at 89 miles per hour or lower. You can see how a strong updraft is 90 to 134 miles an hour. That is air going up into the storm that quickly. A very strong updraft is 155 to 179. And then look at that, an extreme updraft over 181 miles per hour. That is the air going up into that storm at 181 miles per hour. In those extreme updrafts, you can have big, big hail. Now also, we talked about how many times it's going up and down and up and down and up and down. If you could cut a big hailstone in half, you would find rings. Have you ever seen rings of a tree? When a tree is cut down, there are rings in the tree. It tells you how old the tree is. Well, take a look. Our hailstones also have layers. Looks like the inside of a tree, right? If you could cut it open, that's what you find sometimes. And it has to do with this freezing and refreezing and the times that it's been up and down. Here it gets a little wet and slushy. Here it gets a solid layer of ice. Here it gets a little wet and slushy. Here it gets another solid layer of ice. And that's the layers that you see. That's why it has layers. There you go. So that's kind of interesting. So our hail size depends on the strength of the updraft. And you can have a super strong updraft at 181 miles an hour. Also, if the air is going up at 181 miles an hour, do you think it's coming down softly? No. If the air is going up at 181 miles per hour, then you have some very heavy rain, cool, heavy air rushing to the surface. And that's how we have damaging winds. We'll talk about that. I'm going to keep talking about hail here for a minute. So we talked about the layers. Also, did you notice on here that they can be really spiky? See, that's a really spiky hailstone. I've got some more pictures here of that spiky. Look at this. That's a big hailstone. There's a dollar bill and a tennis ball. That is a tennis ball and a dollar bill. And look at the spiky nature of that hailstone. Look at this one. See how spiky it is? Very spiky. And that probably happens, when you're getting so big that when your hailstones are this big, a lot of times, again, it's like when you're going into the freezer to make a cold drink in the summer and you want ice out of the ice box and a bunch of the ice cubes are frozen together. That happens a lot up in these thunderstorms where you get these hailstones that glom onto each other and they end up looking this big. I mean, that could have started as like a golf ball size, and it's got these other stones glommed onto it. So this top one, just to show you again, that's so big, that was in Wichita, Kansas. And it was 7.75 inches in diameter. Take a look. This one was the one in Hastings, Nebraska, which used to be the largest hailstone, but we've had a bigger one. So what about that hail size? So we rate hail when we have spotters that are out there that are taking observations. We usually think about hail size compared to objects like a pea. My brother hated peas when we were growing up. He didn't like to eat peas at the dinner table. So a pea is about 1/4 of an inch. And then you have dime size hail. Quarter size hail, and you all know what a quarter looks like. Quarter size hail is generally when you start to see some damage. 1-inch hail, quarter size hail, that will trigger a severe thunderstorm warning. When you have severe hail that's over an inch, over a quarter. Then you have golf ball, which is almost 2 inches in diameter. Tennis ball, 2.5 inches. Baseball is just under 3 inches. And you can have grapefruit size hail. In fact, we had a hailstorm not too long ago that we were watching here in St. Louis. It was actually a storm up in Iowa, and it produced 4-inch hail. We had a report of 4-inch hail. That is grapefruit size hail. So the largest hailstone, I get this question a lot on my school talks, the largest hailstone on record fell in Vivian, South Dakota, and that was on July 23rd, 2010. It measured 8 inches in diameter. What did I just say grapefruit size was? 4 inches. So the largest hailstone that fell in Vivian, South Dakota on July 23rd, 2010 measured 8 inches. That's like 2 grapefruits sitting right next to each other. It weighed almost 2 pounds. Crazy, huh? All right. So that's the largest hailstone on record. Now, remember I told you that these storms can live a long time? They can live a long time, and they can produce a lot of hail. A lot of times, the storms will produce hail, drop their hail, because the hailstones eventually get what? They get too heavy. Even with a super strong updraft, it can only hold on to all those hailstones for so long, and then the storm drops them, right? And so all the hailstones fall, and the whole process starts over again. But remember, our supercell storms, our severe storms, can last for hours and hours and hours. They have constant access to that warm, unstable, moist air and that constant lift. So they can create more hailstones, and they do create more hailstones. And so you can have several storms that move over large distances, producing a whole lot of hail. And that's what I wanted to show you, because I saw this yesterday and I thought it was really interesting. One of the costliest hailstorms in U.S. history occurred on April 10th, in 2001. And guess where that was? For all of my St. Louis friends watching, this was a St. Louis storm. This storm cut a large swath, a path, along the I-70 corridor, which connects St. Louis and Kansas City, along the I-70 corridor from eastern Kansas all the way to southwestern Illinois. It pounded the St. Louis area. Property damage was in excess of $2.5 billion. Another series of hailstorms pounded the St. Louis area in 2012, causing $1.6 billion in damage. But look at this hail swath. So the one that traveled down the I-70 corridor, I'm going to bring this over so you can see. Let's see, St. Louis is here, right? Kansas City is over in this way. That's how long the primary hail swath was, all the way across the state of Missouri into Illinois, starting in eastern Kansas. So that is one thunderstorm, y'all. One storm did all that. One big storm, just like this, marched from eastern Kansas all the way across Missouri into Illinois, dumping all that hail before it finally died out. I think that's really amazing. These storms, once these storms get going, they can live for hours and they can do all kinds of damage. All right, so that's how hail forms. I want to talk just a little bit more. How you guys doing? I want to talk just a little bit more about the other item that we see in these storms a lot, and that is damaging wind. That's not tornado wind. Tornado wind and straight line winds are a little bit different. So we have our tornado winds that are spinning, And then we have what we call straight line winds going this way. Remember I talked about how heavy this air is? It's cold, it's full of raindrops, it's full of hail, it's full of all kinds of things. Your updraft is going at 170 miles an hour. Your downdraft is racing toward the surface. And you can have downburst winds, which are winds that just shoot out of the bottom of the storm right onto whatever's down here. And that could be a house. There was a devastating windstorm in Dallas. It's been several years ago. I don't remember what year it was, but it hit the Cowboys practice facility in Valley Ranch. The Cowboys used to practice in kind of a tent-like structure that was over in Irving, Valley Ranch. And one of these thunderstorms came right over the top of that tent where the Cowboys were practicing, and wind just came straight down on top of that tent. It destroyed it. So that's a downburst. You can also have winds that come down, they hit the surface, and they go out. And so this wind that's coming out ahead of the storm is what we call straight line wind. And it can create damage. You can have straight line winds, 80, 90 miles an hour. You could have very strong straight line wind. Now the other thing that's cool, and it creates a lot of scary looking clouds, is you have this motion here where you actually start to see the wind curling back up. That sometimes it's called a roll cloud. I don't think I have a picture of a roll cloud. I'll have to post a couple after I'm done with this. How about that? After I'm done with this, I can put a couple pictures up of a roll cloud. But a lot of times you see one of these big storms coming at you, and it's got what looks like a rolling cloud out in front of it. It looks like a UFO or a spaceship. And that's because you've got this rolling motion, and you actually get a cloud that forms. It looks like a tube on its side, and it's rolling like that. So you can have a roll cloud. You can have you could also have clouds that kind of come out this way, and they look really scary, and they can be really low to the ground. Those are called shelf clouds. I've got a picture of one of those. See how creepy that looks? Right in there. It can cover the entire horizon. And that's kind of a creepy looking shelf cloud. And we call them that, scary looking clouds, SLCs, because there is so much happening in the environment of this thunderstorm that you can get a lot of funky looking clouds. A lot of clouds that people mistake for that guy, the tornado. A lot of the stuff, but your tornado doesn't form out in the front of the storm here, does it, usually? So you get roll clouds, you get shelf clouds, you get all kinds of fun stuff, and this is where you have some wind damage. You can have winds that go out, straight line winds that come down, microburst or downburst winds that come down. Your hail usually falls closer to the updraft, and then there's your tornado. A wall cloud's pretty distinct. This one's not the best picture of a wall cloud, but it would be this lowering here. Wall cloud. And then this is a funnel. The reason this is a funnel cloud and not a tornado is, you see, we talked about the condensation funnel. That's the condensation funnel. That's actually a cloud. But notice there's not damage going on. Well, I'm not sure you can see the surface there. You need to see if there's damage going on down at the bottom. So that's a funnel cloud. So those are some of the things that we see around these clouds. All right. That is a supercell thunderstorm. That is how we get severe storms versus your garden variety storms. So just a quick review on that. It has to do with shear, right? It has to do with shear. That's that extra ingredient. Wind shear, which can come in the two different forms. It can come in the speed form, speed shear. Wind speeds increasing with height, tilting the updraft. Tilts over the updraft. Speed shear, when wind speeds are increasing with height, that generally gives us our severe storms where we have a hail and wind threat. But remember, we need that extra ingredient for the tornado threat. And speed shear doesn't give us that. So if a weather balloon finds a speed shear environment, that's generally when we have a severe thunderstorm watch. We'll be watching. If storms go up in that environment, man, they can produce hail or damaging wind. What we need for tornadoes is directional shear. That's winds that are changing direction with height. Because as winds change direction with height, they create a spin in the atmosphere. And you gotta get that spin. Starting horizontally, pulled into the cloud vertically, tilted so that it spins faster, and that produces your tornado at the surface. Or you at least have to have that to get the tornado at the surface. There's some other things that are pretty complicated that we won't get into today that are other ingredients. But essentially it's like this. If you've ever baked a cake or baked cookies, you need all the ingredients just right to have them taste great, right? To have the best chocolate chip cookies in the world, you gotta have chocolate chips, flour, sugar, brown sugar, butter, eggs, vanilla. I like to throw a little bit of nutmeg in mine. So you have to have all those ingredients just right. And then you have to bake it in the oven. To get a tornado, there are a lot of ingredients that have to come together just right, or you don't get a tornado. And like I said, in these supercells, 1 out of 4 will actually produce a tornado. A lot of times we get tornado warnings based on what we call radar indicated rotation, because the radar sees that the storm is spinning, and it is spinning in the mid levels. It's also spinning in the upper levels. Remember, that tilted updraft is all spinning, but the spin that matters the most is the spin down here. And sometimes it just doesn't happen. The ingredients aren't all there. I remember one time Mom and I made pumpkin pies for Thanksgiving. And she thought I put the sugar in the pumpkin pie. I thought she put the sugar in the pumpkin pie. No sugar went into the pumpkin pie. And it went to the Thanksgiving table with no sugar in it. It looked pretty, beautiful pumpkin pie. But if you took a bite of that pumpkin pie, it tasted terrible because it didn't have any sugar. In fact, somebody carved on it, "Do not eat." No sugar in a pumpkin pie, not very good. So if one ingredient's not there, tornado doesn't happen. Everything else looks right, and so the National Weather Service will warn on a tornado because it could happen like that. But maybe it doesn't happen. 1 out of 4. So tornadoes have to, all the ingredients have to be right there. And maybe some of you are future scientists and you can go become meteorologists, go to college. You can take all the classes that are required, the atmospheric physics, some of the math, all that fun stuff that we use to be able to forecast. And maybe you could take it a step further. Maybe you could get a master's in tornado genesis, how tornadoes form. Maybe you could go down to Norman, Oklahoma, where the Storm Prediction Center is. The Storm Prediction Center is a team of meteorologists in Norman, Oklahoma that actually forecast severe weather for the whole United States. If there's a watch issued, it comes from the Storm Prediction Center. And they monitor the United States for environments for severe weather and tornadoes. So maybe you could go down there and work with those folks. But there's still a lot we don't know about tornadoes, and it's why it's very hard to explain. It's very hard to answer the question, how do they form? Because there's a lot we still don't know. So that is all I have on the supercells. Sometimes, Nick says sometimes they happen and no eyes are actually there to see. Yes, because you have to have a spotter out there to see it. So I'm just looking back through here, just saying hi. Hi, Sarah. Hi, Ravi. Who else is here? Tara. My family was in Florida a few summers ago and a storm blew in. We saw someone's tent blow over. Yeah, some of the storms in Florida can be pretty strong. Hi, Keith. Hi, Samantha Jones. Sam's at home. How you doing, Sam? How big is 100-inch hail? Well, it would be 100 inches, wouldn't it? Pretty hard to... Hi, Phoenix. So my sister-in-law and my brother in Texas are watching. Finn and Devin. I love you, Aunt Meg. Oh, I love you too, Finn and Devin. You guys are the best. So thanks you guys for tuning in. I really appreciate it. I have a really good time talking about this stuff, as if you couldn't tell. I didn't quite intend to go this long today. I tried to be really organized with my notes, but I just get pretty wrapped up in it. It's pretty fun. Again, you're welcome to email me questions. In fact, I'll put my email address on here one more time. It's meghan.danahey at KMOV as in Victor.com. I got a couple questions from Tuesday's lesson that I've got to go back and answer today, but there we have, Meghan.Danahey at KMOV.com. So please shoot me an email if you have any questions, or especially if you have any questions over this craziness that I drew today. I love to talk about supercells. I love to talk about storm structure, clouds. I'll post some more pictures on my Facebook page as well. And then next week, maybe a week from today, maybe next Thursday, if you'd like, we can get back together and we can talk a little bit about hurricanes or tropical storms. That's something we can do. I saw some people interested in that. So maybe we'll get together in a week and we'll talk about that. But I'm going to sign off for now and let you guys go back to whatever it is you've got planned for the rest of the afternoon. Thank you so much for joining me today. Thanks for playing along with all this. As always, I like to ask you 2 questions. And the first question is, did you learn anything? The second question is, did you have any fun? If you learned a little and laughed a little, then my job here is done. Thanks so much for tuning in. Have a safe and healthy day.